Welcome to theme 3.1, the first part of magnetism. We're going to kick off talking about magnetic fields, how we understand we can have action at a distance with magnetism. And we're going to talk about the force on a moving charge and the motion of it that results from that, and a device based on that knowledge, the mass spectrometer. We're going to talk about forces in a wire with a current. Might seem like a separate topic, but it's not. It's still charges moving and forces acting on them, so it very much relates to that section before. Then we're going to talk about magnetic dipole moment. We don't define a magnetic monopole because no such thing has been observed. Only magnetic dipoles are observed in magnetism. We're going to go on to talk about the fields generated by a current in a wire. And for that, we're going to talk about a law called Ampere's law. It's one of Maxwell's equations. We've already met a Maxwell equation in terms of Gauss's law in electricity. So here's another one, and that's Maxwell's equations are something you come back to study next year. We're then going to talk on forces between wires that result from understanding the field generated by each of them, and then the field due to different shapes of wires that you can arrange, like loop, solenoid, and a toroid. Good to have a look through Wiley chapters 28 and 29, and it's important to have the course notes open, theme 3.1 then, open, whilst you're listening to this lecture, and that you're annotating on that. There are two ways of producing a magnetic field. Here's one of them. We have a wire with a current passing through it, and if the current's going in the direction I'm showing here, then this is the magnetic field that's generated around it. And if we arrange that wire into shapes, here's a shape of a coil, or a solenoid as it's called, then we can enhance that effect, and all the magnetic fields add up in the center here to give a strong magnetic field. It looks very much like this case below, doesn't it? Which is a permanent magnet. So it's a solid material, and it produces a magnetic field without needing to supply a battery or a circuit to it or current then. Well, actually, the result of that magnetic field is still coming from currents, just currents you can't see. On the atomic scale, if you think of the Bohr picture of the atom that we looked at in theme 1, there are currents, there are electrons going around protons in atoms. So yeah, there are currents, and when they add up in this structure, then on the macroscopic scale, you can think of it like a loop with a current in it, producing this same effect. So there's a direct relationship between the two pictures here. Okay, so there's two ways you can produce a magnetic field. Practically, though, you pass a current through a wire or you use a permanent magnet. We can use iron filings to around something like this, and small pieces of iron like that will be affected by a magnetic field. They rotate in the magnetic field, and we can look and analyze the fields using something like that. There's a magnetic force. If we had a moving charge in this region here, that would be exerted on that charge, and we could look at the forces on that, and again analyze the field in that region as a result of that. Ultimately, then we can use a magnetic force to define a magnetic field, and that's what's done for the definition of field strength. The direction of a magnetic field can be mapped out using a compass. This is where a compass needle would point at different positions on that field. A compass needle consists of a magnet that's free to rotate. So a compass needle has a north and a south pole, and the north pole of the compass needle would be at this end here, and the south pole at this end, relative to that arrow direction then. So the arrow points from south to north for that, what is called the dipole of that compass. Okay, so we define here the direction of a field using a compass in that way, and this is the same for the Earth then. So a compass on the surface here would point in the same direction as this guy is pointing there. And it's because of that direction of the needle pointing upwards there that we refer to this end of the Earth as the North Pole. It's the direction towards which compass needles point. The North Pole of compass needles then point in that direction. So we call it the North Pole. It is confusing because in actual fact, it's the South Pole of the Earth's magnetic dipole. But there we have it. That's historical, and we have to live with that now. Iron filings can show the pattern of magnetic field lines Here we have a Perspex sheet and we have a magnet below it. And we've put iron filings on top and shaken things around a little bit. The iron filings naturally arrange themselves like this. So that's the North Pole, South Pole of the magnet. See the field lines follow these patterns around. And you can also see some field lines are present inside the material as well. If we were to maybe do a better experiment there, we'd see that we get these field lines continuous through the material there. So all the field lines here actually do go through the material. They're not just outside the material. All magnetic field lines are continuous. There's no beginning, there's no end of a field line. And this is a very different situation to electricity then. When we think of an electric field, an electric charge, there is a beginning and end to field lines. They certainly start from a positive charge, don't they? And they certainly end at a negative one. And that's because there is such a thing as an electric monopole, a charge. But there is no such thing as a magnetic monopole. We only find magnetism existing where there's a north and a south pole in a dipole. Okay, so let's arrange the south pole of a magnet next to a north pole of another one, and the field lines we'd expect to go from north to south like this. Looking like this with iron filings then. So it's a very similar pattern, isn't it, to the dipole pattern for a field that we saw with electric fields though. So there is an analogy here between dipoles in electric fields and magnetic fields around a magnet then, or between magnets. And here we've got two north poles of a magnet, so two like poles. It would be similar for two south poles, but the vectors would be in the other direction. And with two north poles, the fields, they don't cross. But they must begin and end somewhere. So eventually this field line, even though it seems like it's going off to infinity, it might go far away, but at the end it must return ultimately to come back to that magnet. A field line coming out of the page is defined as a dot. A field line going into the page is defined as a cross. And this way of defining field lines is exactly the same convention as with any other fields, whether it be electric field, velocity force, magnetic field, whatever. Also common with any other fields is that we can use the field lines to work out both the strength of the field and the direction of it. The direction of the field at this point P is that it's tangent to that field line at that point. So it's a grazing incidence with it. And so we can draw a vector at point P like that for the field at point P. And we could talk about the magnitude of that vector by looking at the density of lines around that point. The greater the density, the greater the magnitude of the field. So they've got a longer line there than we have for Q. That's meant to be tangential, and it's a shorter line there because there's less density of field lines in that region. It's good to have some similarities with electric fields, but that's just about where it ends. This is the equation that describes the force acting on a charge Q due to a magnetic field B. And you can see that the force marked here is not in the same direction as the magnetic field. That's what we experience when a charge moves like that relative to a field. It's at right angles. It's at right angles to both. So if we draw a plane that contains the magnetic field and the velocity, then it's at right angles to that plane. It doesn't matter what theta is to do that. But if theta was zero, if the velocity was along the direction of the field, we find that there's no force acting on that particle in that case. Okay, this turns out to be a cross product. We can write this as F equals QV cross B. And if we write that out in this form, magnitude of Q, speed, magnitude of B, turns by sine of the angle that subtends between B and V. Then we can see that when theta equals 0, sine theta is 0, and the force is 0. So there has to be some angle, theta, between B and V to experience a force, but if there is, it's at right angles to the plane that contains them both. Okay, so that's really then very different to the force that's experienced by a charge in an electric field, which was in the direction of the electric field and also didn't contain anything about velocity in it. So, if this charge is stationary, there's also no force acting on it. We can define a unit for magnetic field. 1 coulomb charge going at 1 meters a second, and where we measure a force of 1 Newton acting on that charge, that means there's a magnetic field present of 1 Tesla. And that's how we define or can define magnetic field. Let's just go over this general idea of a vector product where C is A cross B. Then C is the magnitude of A, magnitude of B times sine of the angle between them. There's A and B there. There's the angle between them. And we consider sweeping out, going from the first to the second here, the first vector to the second, which is from A to B here. And that sweeping out gives us the direction of our fingers on our right hand, shows us the direction of our thumb, which is the direction of the resultant. There's another way of seeing that direction. That's with the standard screw rule. If you were to sweep out in the same direction here as this arrow, a standard screw thread, so any screw or any tap or anything you use in everyday life, then it would travel in that direction. And that's irrespective of whether the point of that screw is pointing upwards or whether it's pointing downwards, it still travels upwards. And so I find that quite a useful way of visualizing the direction of this resultant C. I find it much more useful than the first rule, but it's really up to you what you find works best. The bottom line is that you do need to be at ease with this idea of a cross product, and you do need to be at ease with determining the direction very straightforwardly. And if you're not, maybe have a click on this link or look at other online references to just get yourself a bit more comfortable with cross products. You will need them to understand this magnetism thing. We have here an old style TV tube where electrons are fired from the back to the front, and there's a phosphorus screen. They're going at this speed. We have a magnetic field generated by coils at 60 degrees to the x-axis in the xy plane. We're given that value and we're given the angle. So we're asked to find what is the force on this electron. So it'll be deflected by that force. So first thing, what is the direction? We take V cross B, sweeping that vector red to green through that angle in the xy plane. And the resultant of that is upwards, the right-hand screw rule. But we've got minus E times all of that. So we've got minus of a vector that's upwards, so that's a vector that's downwards of magnitude given here, modulus of Q written here, but that's E, times by VB, and then sine of this angle, sine of 60. So when we write that all in, we get the magnitude of the vector, and we've already worked out it's directed downwards, the negative Z direction. A positively charged particle, stationary, constant magnetic field. Which one of the following concerning the particle is true? It doesn't move, it accelerates, direction perpendicular to the field, it will accelerate in direction parallel, accelerate in direction opposite, it will move with constant velocity in the direction of the field. Now, which one is true? If it was an electric field, you'd expect it to start to move in the direction of the field. So it would be B. It would accelerate in the direction of the field. Now, that's if it's an electric field. This is not an electric field, it's a magnetic field. So we should apply the equation for a magnetic field. Q, V cos B. So this is what we have. Four things in it then. It's not just Q and B, as it would be for an electric field. We've got a velocity to think about and an angle to think about. Well, the velocity is 0 here. It's stationary, so it will not move. A region contains only a magnetic field. An electron traveling east experiences a vertically downward force. What is the direction of the magnetic field? Is it upward and away from the Earth, downward towards the Earth, due north, due west, due south? We need to get our tools together. So here they are. It's our cross product of vectors, and this is the thing worth remembering. F equals Q V cross B. Well, if it was a positive charge as shown there, then we'd have a positive in there. V sweeps to B and the force is upwards. In fact, we've got an electron, that's a negative charge, so it would be the opposite direction as shown in this diagram. It would be downwards if that was a negative as shown there, which is actually the direction that we're told the force is acting. So this is a very directly relevant diagram. So we've got a downwards force on an electron, and we would have a B and a V like that then. Well, we're told that the velocity is due east. So if that's east, then where the red arrow is pointing, then the magnetic field would have to be north. So it would be C. So electric and magnetic fields affect the charge very differently. But we ought to put a qualifier in here in saying that the two fields, although apparently very different, have been unified under one understanding. We can explain just the idea behind that unified theory here without going into the maths. It comes from the idea of Einstein's special relativity, that things in relative motion experience a relative contraction. That's going to be true for very fast things as much as it's going to be true for everyday relative motions. It's just the contraction is going to be so slight in everyday relative motions, it's not something we give a thought to normally. Let's consider the postulates that Einstein laid down. And he said that experiment in any inertial frame results in the same observables. So if you do an experiment on a train or on a stationary lab, you're going to get the same results of what you see. He also said that light has the same speed in all directions in any frame of reference. So it's always 3 times 10 to the 8 meters a second. And from that, he came up with this, that the new length of an object equals the original length times my root of 1 minus v squared over c squared, where v is the relative speed. That was originally called the Lorentz equation because it came from another method originally by Lorentz, and Einstein was able to show that these postulates led to this equation. Anyway, it applies to everything as far as we're concerned, and it's going to apply to a current in a wire. So if we consider electrons flowing in a wire here, we've got a current. In fact, the current's to the left, right? And it generates a magnetic field around it, as we've been talking around currents in wires, and it comes out of the page like this and into the page over there, goes around it. And if we consider an electron moving along with those electrons at the same speed v, and we do v cross b, it will be a vector downwards. Have a go with that with your right-hand rule or screw rule, whatever works for you. And we take minus that because it's a minus e that's moving. That's the charge. Then it's a force upwards. So this electron would be attracted towards the wire. That's the thing we'd observe in the lab frame. We wouldn't observe any electric fields emanating from this, just a force towards the wire. And so we have to evoke the idea of magnetic fields, right? Okay. If we now consider moving with the electron in a different inertial frame, we'd be going at the same speed as this current now of electrons that are moving. And because this electron now is stationary in our lab frame, we couldn't see a force due to a magnetic field. There's no V there, there's no V cross B term, but there'd still have to be a force that we observe. So to reconcile that idea, we need to consider this special relativity. And what we see, the electrons were contracted before in our previous frame of reference, are now further apart. And the cores, the atomic positive cores in the metal, which weren't contracted relatively before, are now going to be closer together. And this is both coming from this idea of the Lorentz contraction. Well, there's an overall positive charge there in that volume. And so now, moving along with the electrons in the wire, we could say we do experience an electric field, and we do experience that force. So that force there needs to be the same force we experienced there. What we're saying is that what was due to a magnetic field, if you change your frame of reference, can be considered to be due to an electric field. So certainly we can say we've unified the ideas of electric and magnetic fields with this idea. It's a very small speed that electrons move in a wire, only millimeters a second, right? But if we consider the Lorentz contraction that comes from that, 10 to minus 3 meters a second, 10 to the 8 there, we've got 10 to minus 11 there, and when we take 1 minus that square root, it's 1 minus a half, 10 to the minus 22. In other words, the change in length is around 10 to the minus 22 as a fraction of its original length. You might think, how can we observe something like this? Well, if you just think back to theme 2, we were saying a Coulomb charge is enough to lift the most laden oil tanker where it's 1 meter away from its opposite charge. Tremendous forces for any imbalance in charge. And if you consider the density of charges in a metal, free carriers, roughly 10 to the 23 a mole, right? So, and a mole of metal is only going to be 50 grams of it or so. So it doesn't take much length of wire before you have an awful lot of electrons contributing to a force when you consider a slight imbalance in charges in that volume. So it does all work out in the maths that it does reproduce the same value of force. And it is one of the greatest achievements of the last century to unify the understanding of those two fields. Nonetheless, that all said, in everyday experience, we wouldn't want to be going through special relativity to try and understand a force being exerted on a charge by a wire, right, with a current in it. So we use this idea of magnetic fields, and it's just as valid idea as electric fields, really. And it's very useful to consider them as different contributions to the motion of a charge, in that the phenomena observed to be so different in our everyday experience. And indeed, we're going to bring this equation together with that equation for adding in the total force of an electron in any situation where electric fields and magnetic fields are observed to be present. Let's now consider the motion of a charged particle in a uniform magnetic field. Here's our uniform magnetic field directed into the page, those green crosses. Got a positive charged particle. If at the bottom there its velocity is to the right, then the plane that's made with the velocity in B has to be perpendicular to the direction of the force. And if you can just practice your V cross B as we're talking here, whether it's the right-hand rule or whether it's the screw rule, it's a force that's upwards. There's a reminder of where we were earlier. So you can take it from that to that. Over here, the plane formed between V and B is this one with my pointer, and the force is to the left, perpendicular to the plane. And likewise here, there's that plane of V and B, and the force is perpendicular to the left. So the force is always to the left. It's a constant force. It's not changing because Q, V, and B, and the angle between V and B aren't changing. So it's going to give circular motion. When you have a constant force, it's always directed to one side of a particle. They give you a motion with a radius r, where the force is given by mv squared over r. So that's from first semester. I hope you can remember centripetal motion. Just bring that forward. Go back and look at that if you want a reminder. But it has to equal this force then, QVB. Because V and B are perpendicular to each other. Sine theta is 1. We can rearrange for the radius of that motion. The bigger the mass or the speed, the larger the radius. The bigger the charge or the magnetic field, the smaller the radius. We could consider how long it takes to go around once, called the time period of the motion. It's the circumference, distance in one revolution, divided by the speed. R over V, if you just rearrange there, it just gives you m over qb. Well, we want 2 pi r, so we've got 2 pi there as well. And you can see that that doesn't depend on the speed of the particle or the radius of the particle, just on the mass, the charge, and the magnetic field. For an example, we've got an arrangement like we just talked about, and we have electrons accelerated through 350 volts. So we could work out their speed from that. And we have a radius of the motion. Well, let's work out the speed, how we express that. Conservation of energy, the potential energy that's been released through going across 350 volts will go to kinetic energy. So we can write this. Rearrange for V. And we can put in the charge of the electron there, 350 volts there, and the mass of the electron there to find the V. Okay, well, we want to find the magnitude of the magnetic field. We have this from the previous page. Rearranging for B. We get that. We need to put V in here. So if we find V, then slot it in. V turns out to be 1.11 times 10 to the 7 meters a second. And we get this for the magnetic field. That speed, incidentally, is not getting too far off the speed of light. It still is 1/30th the speed of light. And we don't consider relativistic corrections or complications for speeds up to that sort of speed. If it was getting close to the speed of light, though, we would have to strictly consider special relativity. But that's not something we consider in this course, then. We're sticking to non-relativistic physics in this course. Let's consider the motion of a charge in both an electric and magnetic field now. We've got here a region where magnetic field is directed into the page, that's the green crosses, and the electric field is directed across from left to right there between two charged plates. We've got electrons from a source here that are collimated by using a slit, and they pass along between in that region. So they're going to experience a force due to both. The electric field force is going to be to the right, because F equals QE, due to an electric field. And the magnetic force is going to be to the left, because we have V cross B, and B is directed into the page. That will be in this direction. I hope you're feeling comfortable with whatever method you're using to determine that. But there it is as written. The magnitudes of those two forces then are simply QE, where is the magnitude of the electric field, and QVB, because V and B are at 90 degrees to each other. Okay, so we got an equation that describes the force on a particle due to electric field and magnetic field being present. And it would be an equation you could apply no matter what the direction of the electric or magnetic field. Well, as shown, they're equal and opposite, though, these two forces. And QE has to equal QVB if we have an electron that goes in a straight line, as shown along that dotted line now. So, cancelling the Q's, V equals E over B. Only particles with this speed will pass straight ahead, and if you have a slit up here, would pass through that slit and out of the device. Only particles with a ratio of E over B for their speed. Particles that are going faster would not pass, because FB would not equal FE. Particles that are going slower wouldn't pass. So what we have here is a velocity selector. J.J. Thomson confirmed unambiguously the nature of an electron in the late 19th century with this apparatus, a vacuum tube, very much like a TV tube, with an electron beam collimated through a slit here, ending up on a phosphor screen. And before it goes to it, going through a region with a magnetic field, here pointing into the page, an electric field directed from top to bottom between two plates. Well, the force due to the electric field would be upwards on the electron because it's negative charge, opposite to the electric field then, EE. And he was able to show that the force acting on the electron due to the magnetic field as shown, which we now know as V cross B, right? V, there's the velocity to the right, B downwards gives you a vector that's upwards, but it's minus in front because it's minus E, given overall a vector in that direction of EV cross B. These are in opposite directions, and so if you adjust the magnetic and electric fields, as we were talking about before, you can get the electric field to go straight ahead. So he was able to confirm that, and in doing so, confirming the nature of an electron's behavior in a magnetic and electric field. This is the equation that we use to describe the behavior of an electron in both fields then, or any charged particle. It's called the Lorentz force, sometimes called the electromagnetic force, and it's then a complete description, more complete description of the description of a force on a charged particle. A velocity selector is a key component of a mass spectrometer. There it is. It's this guy here. We've got charged particles that we want to analyze coming in here. And we've got an electric field going across, a magnetic field going into the page, magnetic field B, electric field E. We can select the velocity that makes it out the far side, and goes straight ahead then, by setting the ratio E over B to what we want. Once we've selected the velocity of particle we want, it's very useful for a mass spectrometer because the particle then travels into this different region here with a different magnetic field, B0. And we've said that in the absence of electric fields, that it will undergo a circular motion. So there it goes. And now the circular motion can be worked out by equating the centripetal force to the force on that particle. We can rearrange that, put m over q on the left, and r b naught over v on the right. So that's b naught. We can put v in now for our velocity selector. And we've put that all together, m over q is r b naught times by b, the value in the field in the velocity selector, divided by the electric field in the velocity selector. We can set b naught, b, and e. There's only one thing we're not setting, and that's the radius. That's going to depend on the mass of the particle and the charge in it. Well, these particles will be from a sample that you ablate in some way, and the parts of the sample, fragments of the sample, become ionized, generally singly ionized. There might be some doubly ionized particles there as well, but one's able to disentangle that. So take it for the moment that they're singly ionized, then we can learn about the mass of the fragments that are coming off the particle. And that then informs us about the constituents in the sample. We can analyze the sample. It gives us a fingerprint. It looks something like this. Here you see on the horizontal axis m over z. Z is q in this case. So mass over charge. And that's what we read for our mass over charge, and that's the relative abundance. And what we're doing there is literally reading off from a linear ion detector along that plane there. It's very straightforward to read off the readings along that plane of ions that you're detecting and just present it on a graph. And that's a mass spectrometer. Looking at this example, try a low velocity particle, and you can see it doesn't make it through the velocity selector. A high velocity particle doesn't make it either, and the right velocity particle is balanced, gets through. If we look now at different masses at the right velocity, a heavier mass, larger circle, and a larger mass, an even larger circle. So they're going to be detected at different positions on that detection screen here, depending on the mass. Let's now consider the force on a wire in a uniform magnetic field. Now, we've considered the force on a charged particles, QV cos B. We know from theme 2 that current is the rate of flow of charge, so we can write the amount of charge that's passed by any plane and as time t as being it. And that time times by the speed of the charge flows, the length that's been covered in that time. So we can replace t by length over the drift velocity. Well, that means we can replace QV by IL. And there we have it, IL in place of our QV in the original equation. That's now the force on that group of charges in that wire then, that current. We can consider straight wires with that, that's fine. Or if we have a wire that has some profile to it, we would need to consider the contributions of force to that wire for each little bit of the wire, each little dl. So we'd write it like that for a little bit of df. We'd have to integrate up the force over the whole of the little dl's cross b's. So if different parts of the wire were at different angles to the field, you'd get a different force contribution from that part of the wire then. We don't need to integrate to find the answer. Straightforward though enough for a straight wire. No integration required for that. We have here a circuit with a battery in it, positive terminal top, negative at the bottom. The current will go clockwise, positive current. We have that wire passing between a north and south pole of two magnets there, or one magnet. And we're asked, what is the movement of the wire between those poles? In which direction would it go? Would it go towards the north pole, towards the south pole? Would it move upward towards us, or downward away from us? Well, the wire doesn't move. With the aid of the relevant equations, we got a current going from P to Q. Cross product of that L in the direction of the current then, going from P to Q, with B going from the right to the left, would be a resultant vector that's downwards into the page. So the wire is going to move downward or away from us. It's going to be D. You could also see that from just thinking about the charges moving. You think of current direction being the flow of positive charges, then we got charges moving from P to Q. And it's the same deal then to think in terms of that equation to answer that question. We have a circuit, it's currently open, the battery positive terminal there, so the current will flow in this direction once we close the circuit. It'll flow into the page there along that wire between these poles of this magnet. We've got north-south at the bottom, south pole at the top. If we look at the field lines, they're going then upwards. What direction is that going to go? That little swing of wire there. Well, take the cross product, IL cos B or QV cos B. We said the current was going into the page, so that's the direction of that vector. Cross, well, it's upwards. So that gives a rotational sense in that direction as shown. The screw rule means the screw would go to the right. Or whatever method you use, we expect that little swing of wire to go to the right. So should we try that? And there it goes. We can swap things around. If we flip the battery, the current will go in the other direction. We'd expect the cross product to have the opposite direction result, and it does. If we flip the magnetic field lines, same thing. We'd expect the cross product to have an opposite direction. So let's flip them now, and it is. Here's the essence of a DC motor. We've got a positive terminal of a battery there, current flowing this way as per the black arrow up to this brush here, contacting with this commutator, the blue guy, and so the current flows as per the black arrow there. If we look at the force on this wire, QV cross B or IL cross B, V is to the right for the positive charges, magnetic field is downwards, so V cross B is a force in green arrow as shown, and it's equal and opposite at the bottom because the current's in the opposite direction. Just play that through, we see it turning. We swap each half turn, we swap the polarity of the current by having two separate brushes there, the blue and the red. And if you can see the current to the right there, if that went to the bottom, it would be to the right of the bottom, giving a force in the opposite direction, right? So we want to swap that halfway. At this point, we swap them. And so when we get down to the other side, we've still got the same direction of current around the circuits clockwise, given the same forces of turning. That means every half turn, we continue to turn in the same direction. Let's consider the forces and torque on a loop in an external magnetic field where the loop's carrying current. Here we see two views of the same loop. Here the loop is showing a clockwise current. We can define an area for that loop that relates to that current direction by the right-hand screw rule. If we look at this other view here, that's the normal to that area there. Now the magnetic field's going into the page there. You see it going to the right there. So we're viewing it from the side. Where I've put the eye here, this is the line of sight for this second view. So we're looking here with this eye into this C point, which is the axis of rotation. So we're looking along the axis of rotation with this second view. And you can see the rotation arrows there. Okay, so we've defined an area. We've got a length A, a length B. It's a rectangle, it happens to be. And we've got four forces acting on this thing. So we've got nice straight sides that we can consider in straightforward calculation. Well, first to note is that by symmetry, that F2 has to equal that F4, and that F1 has to equal that F3. The net force on this wire loop is 0. It's not going to go anywhere, but there's going to be a torque on it. It's easier to see that with the second view. We've got an F1 and an F3 that are going to see those forces go to the side of that axis of rotation so that they don't pass through the axis of rotation, at least not most of the time. And that happens when theta is bigger than 0. So we're going to get what we'd call a force couple, like turning a tap, on that loop where theta is bigger than 0. But when theta equals 0, they're in line, they're not turning it at that point. If it was a motor, it's only the momentum of the motor that carries it through at that point to go to the other side. Okay, let's look at the forces then. Well, we said F2 equals F4 and F1 equals F3. And F2 and F4 also pass through that axis of rotation. They're not going to contribute to any torques, and we've already said they're not going to contribute to moving our motor, so we can ignore them. F1 and F3 are what's left. The values of their forces are given by IL cross B. And if we look here, I times by L, which is length A here, cross B into the page gives us a force in that direction, and it's the opposite direction for the other direction of current. So indeed, it's IAB sine 90, which is IAB. So that's the value of those two forces. And as we said, we've got to consider moments or torque. The moment of each of them about that point of rotation is the length here, b by 2, times by sine of that angle, sine theta. And for intuition on that, as we say, when theta goes to 0, they pass through the axis, so there's no torque. So that is as you'd expect. Got to add them both together to get the resultant torque around the axis of rotation. So we've got these b by 2 sine thetas times by the value of the forces, which are IAB. And putting that all together, then we get that for each one. Adding them together, we get IAB sine theta, which is the area then, we call it capital A, of the loop, times by the current, times by B times by sine theta. Well, that's just for one loop of wire. If we continue to loop the wire around and around and around, in the same circuit now, supplied by the same battery, right? So we had n loops, capital N loops, then we'd get n times the torque. So this would be relating to a motor then. Circular loop of wires placed in a magnetic field such that the plane of the loop is perpendicular to the magnetic field as shown. It's connected to a battery. The connecting wires are close together so you can ignore them, the separation. Which one of the following statements is true? The magnetic force exerts a net torque on the loop. Magnetic force exerts a net force on the loop. Well, I hope we can already discount B without thinking. The magnetic force exerts both a net force and a net torque on the loop. No, then. The magnetic field has no effect on the loop. So it's either A or D. Let's consider now, we've got a current going around here and it's symmetric. It's coming back and we're going to ignore this separation. So going away from us, consider the current going away And the cross product of something going into the page then, and that upward vector would be a force towards the center of the loop. If we consider it coming towards us on the other side, it's equal and opposite, right? Cross product of that coming towards us and a vector that's going upwards is a force again towards the center. So that's going to be true at every point on the loop. And we can ignore the separation of these wires, so we'd expect an overall compression of this loop. We'd hope it was structurally strong enough to resist that compression, right? But it's not going to be a torque on the loop. It's not going to rotate it. This is the case where sine theta equals 0. It's the case where there's no net torque on the loop. So we had a choice of the magnetic field has no effect on the loop or it has a net torque on the loop. And the answer is D, no effect on the loop. A loop in an external magnetic field has a torque on it given by this. We simplify that a bit by calling NIA the magnetic dipole moment. And when we do that, we get torque equals mu B sine theta, or mu cross B. We can also talk of the potential energy associated with this loop. It's U, the potential energy equals minus nu dot B, or minus nu B cosine theta. It makes some sense to define it that way when you think of two examples. Here we got nu anti-aligned to the field and with the field. In this orientation, it wouldn't rotate anywhere. That's the case we thought about in that previous question, where theta equals 0, there's no torque on it. Anti-aligned to the field, it's also true there's no torque on it. However, if this was rotated over to here, so the normal's pointing to the left, we would have these two forces pointing towards the center of the loop. And just the slightest touch on that loop would make it unstable and cause it to rotate. So it is with this guy here then. When you're not anti-aligned, the dipole moment's in the opposite alignment of the field, just the slightest touch and it's going to flip around and release that energy it's stored. So this has a higher stored potential energy and that has a lowest potential energy. Minus mu B cosine theta, 180 degrees, that's minus 1, gives you a positive number for this. And where that's 0, gives you a negative number. We've been talking about the force that acts on a charge that moves in a magnetic field, or the force that acts on a wire that carries a current. It's a similar thing. But we said in the start that a wire that carries a current is one way of producing a magnetic field. So let's look at that here, the magnetic field due to a current. We have a current going in a wire into the page here. We put iron filings around it and tap the iron filings. Then they're going to arrange themselves like this, showing that there are circular field lines around that. You certainly would expect some sort of cylindrical symmetry around a straight wire. And there can be no beginning or end for a magnetic field line, we've said, so it has to be circles. If we put compasses around that wire and see which way the needle is pointing, that's with the current off. And then when the current goes on, they align like that, toe to tail. So with the current going upwards, they align like that. If you switch the current to go in the opposite direction, they'll all switch around. So there's a certain right-handedness to that. There's a direction of a vector, and there is the direction of the magnetic field. We find that the magnetic field decreases with distance from the wire, r, and increases with current in the wire. And then there's some constants here, one of which is called the permeability constant, mu naught. Mu naught is exactly 4 pi times 10 to the minus 7 Tesla meters per amp. Okay, well, if we draw the field lines, as I said, they're decreasing with radius, so they're going to get further apart as you get further away from the wire. A law that relates the magnetic field to the current that produces it is Ampere's law. It's one of Maxwell's equations. You come to it in second semester, so this is the first time you meet it, but it will return. This is it stated. The integral of BDS around a closed loop, which is a line in this case, and that's little bits of length, equals mu naught times by I enclosed. So here's our little bits of length, ds, and it's a closed loop, and it encloses two currents there. One is a wire that's current's coming towards us. One here is a wire where the current's going away. This wire outside I3 is a current that's coming towards us. The enclosed current here would be just the currents that are in the loop, I1 minus I2. They're in opposite senses. So whatever loop we choose, the right-hand side is always going to be the same. That means this line integral is always going to be the same. This mu naught is again the permeability constant given by 4 pi times 10 to the minus 7 Tesla meters per amp. It's reminiscent, isn't it, of Gauss's law, this. And not to be muddled up with it, of course. We're using dS's here to represent little bits of length, not area. And this isn't a charge divided by epsilon naught as it was before. It's a current times by another constant. Of course, this is a different field. It's a magnetic field, not an electric field. So, yeah, not to be muddled up, but there are, it is reminiscent. And you can sort of see why Maxwell gathered similar types of equations together across electricity and magnetism. They had a certain elegance in how they related to each other. We could, in principle, use a computer to add up all these ds dot b's around the loop. So that's b ds cosine thetas. Could be quite a complicated integral to do, couldn't it? Looking at this, the loop's not been chosen to help with symmetry or anything here. It's completely random. Normally you would choose a loop that makes your integration easier, and then you could talk of an integration and solve it on paper. Once you found, anyway, this sum of BDSs by whatever means, then you can determine the enclosed current because it's going to be equal to mu naught I enclosed. We just need to be careful about signs then. We've taken a positive ds here to be in this direction. So we've got a loop integration in that direction. That necessarily defines what we mean by a positive current too. Taking that right-hand sense, if we were turning a screw that way, the screw would come out of the page towards us. And so it defines a positive sense of what is meant by a positive current then as being out of the page. So we take I1 to be positive in this example and I2 to be a negative contribution. Had we chosen ds to be in the other sense, well, that would define a positive current as being into the page. So as long as we're just careful with those signs, then it all works out nicely. So in this case, I1 is considered a positive contribution, and we take away I2. And that's the enclosed current. And notice I3 doesn't contribute at all. It is outside the loop. Let's return to our current carrying wire, and let's derive the magnetic field as a function of distance and current in that wire using Ampere's law. We'll use symmetry to our favor here. We've got cylindrical symmetry, so we'll choose an Ampere's loop that also has cylindrical symmetry, a circle. Is at a constant distance r from the center of the wire. We can take our ds's in any direction we choose. If we choose it this way, then what we're showing for I coming up towards us there is also then defined as positive. We can draw B in here as being in the same direction as ds. If our value for B came out to be negative, we'd know it'd have to be the other direction. But there's one thing we do know, is it would be around a circumference like this, around a circle, the B field, because we've never seen magnetic monopoles. Never been observed. So we wouldn't expect it to be radially outwards, like with an electric field. That would only happen if you could have a beginning of an electric field, a source of it somewhere. We don't see that with magnetic fields, magnetic materials. Okay, so we've got this circular symmetry, and we've established quite a few things there, including that the B field has to be either that way or that way. Okay, from Ampere's law then, integral of BDS is the integral of BDS cosine theta because they're in line with each other. We can take B outside because it's a constant thanks to our symmetry. Integral of ds is just the circumference, 2 pi r, and that equals mu naught times I enclosed by Ampere's law. Well, it's just I. So we can rearrange that for B equals mu naught I over 2 pi r. Now Ampere's law holds true for any closed path, but it makes sense to choose a path to help solve a problem. Again, very reminiscent of the sort of thought processes that went with Gauss's law in electricity, except beware, we are not talking about the surface here, even if we are talking about ds's. We're not talking about a charge either, or an electric field. Let's just take this to the next level and look inside a wire and see what the magnetic field is for that. Again, we use symmetry and draw our Amperian loop as a circle at a constant radius r. Capital R is the radius of the wire. Take out the s's in the same sense, our b's in the same sense. and do our integral. Integral of BDS, again, symmetry helps us here with cosine 0. B comes outside again, thanks to symmetry. And we get 2 pi RB again. So it's the same deal, actually, in that it depends only on the enclosed current. But what is the enclosed current? That's the thing that's different here. It's not a constant. The enclosed current is going to be the total current times the ratio of areas, the enclosed area over the total area. And that's for a constant current density over the wire. So it's going to be this for the enclosed current. So we can replace enclosed current with this guy. There we have it. And rearrange for B, and we get this. Turns out to them be proportional to R. And if you just look at here this graph, we're showing it here. B is proportional to R up to the radius, gets larger and larger and larger. Then outside the wire, it decreases in 1 over R. Copper cylinder has an outer radius 2R, and in radius R carries a current I. Which one of the following statements concerning the magnetic field in that hollow region is true? Well, answers A to D concern finite magnetic fields, and answer C, the magnetic field within the region is 0. I'm going to focus into answer E. The reason for that is that Ampere's law cuts the mustard. Any Amperian loop we choose equals the enclosed current times a constant. We can choose our Amperian loop to be in the hollow region. And then just before, we could do an integral around that and apply the same arguments as to what we'd expect to the nature of our B field to be. It could only be that if there's no enclosed current, that B is 0. So it has to be answer E. Here we have 2 long straight wires. They're parallel. The currents are coming towards us for both wires. We're asked, which one of the following expressions correctly gives the magnitude of the total magnetic field at the origin of that system? So there is the origin. Okay, well, if we draw in the contributions to magnetic field from both of those and add them up, this is what we need to do. This is B1 due to this wire here. And note the sense of that is in that direction, that right-hand rule or screw rule in relation to that current. B2, same thing, same sense, but at that point it's going to be downwards. Equal and opposite to B1 as shown here then. So there are equal and opposite contributions to the direction of magnetic field at that origin point due to each wire. If we add those 2 contributions together with a vector addition as you do for any field, the net result is 0. So the answer is E. Here we have 2 long, thin wires, both carrying a current in the positive Z direction. This first wire carrying 50 amps crosses the x-axis here at 5 meters. This other wire carrying 40 amps crosses the y-axis at 4 meters. And we're asked, what is the magnitude of the magnetic field at the origin? So this is very similar to the last question in concept, but it's more difficult to do because it's a 2-dimensional vector addition we need to think about. Let's just have a look at that. It's always a good idea to redraw diagrams, make them simpler. We can look from above with this diagram, and that certainly simplifies things. We've got these currents coming out of the page now, I1 and I2. We're calling this wire 1 here, crossing the x-axis. I1 equals 50 amps, R1 equals 5 meters. Calling this wire 2, crossing the y-axis, current I2, 40 amps, distance from the origin 4 meters. Now we need to consider at the origin what the magnetic field contributions of these 2 are. And again, it's worth drawing another diagram first. So if this is our x and y coordinates, just to refresh things, the contribution from I1, well, it's coming out of the page. And by the right-hand screw rule, if a screw was coming out of the page, you'd be turning it in this sense to do it, right? So that means its magnetic contribution to that point would be downwards, and that's B1. If you were taking a screw out of a page here where I2 is, you'd be turning it that way, the screwdriver, and the contribution to the field then is to the right of the origin. So there it is. You can see why I like the screw thread rule. It's so easy to relate directions to senses of rotation that way, whichever direction you're looking at it, and you don't have to get your hand up and start turning in all sorts of funny angles to do it. Okay, so we've drawn our 2 diagrams. We can now add those vectors, like any field vectors they add. B1 plus B2, that'll be the resultant vector, B net. Well, it's not too difficult to do that then. It's just Pythagoras' theorem to find the magnitude. You add the squares. We'll be taking the square root. We need to find the values of b's, of course, and there they are for the two of them. mu naught I1 over 2 pi R1, mu naught I2 over 2 pi R2. Now we can add those together, or the squares of them together. And we get that. We can take mu naught over 2 pi root with that, and just adding 100 to 100 square roots, and the answer turns out to be 3 times 10 to the minus 6 Tesla. So that's answer D. Let's consider two long straight parallel wires carrying currents, the force between them. We've marked here the force of wire 2 acting on wire 1, F1, and by Newton's third law, that has to be equal and opposite to the force of wire 1 acting on wire 2. Newton's third law applies to everything. It doesn't matter if it's action at a distance or not. Okay, so what is this force of attraction, as we could call it? Well, we've got force is IL cross B, and the direction of the current is at 90 degrees to the field here at this point marked. The field, due to this wire down here, would be in a sense shown by the green arrow from the right-hand rule, and that would be at right angles to the current there then. So it's just ILB. Well, IL times by B, what is B? Is mu naught I2 over 2 pi A for this value of B2 there. And putting that together, we can see we've got I1, I2 there over 2 pi AL with a constant, the permeability constant in front. So we could talk of a force per unit length, which might be a more useful sort of thing to talk about for wires, depending on the two currents and the distance between them. It goes as 1 over A then. Okay, so the force is attractive, it's positive, if the currents are in the same direction. So you could achieve this by having a battery split into two wires and then back to one wire. Right? And these two wires are going to stick together when you flick the switch. It's a repulsive force, though, if the currents are in opposite directions, because if this I2 was flipped, say, B2 would be in the opposite direction, and by doing that, we make the force upwards and away from I2, and an equal and opposite for the other one. Nothing beats a demo. We've got two wires connected in parallel here, so when that switch is flicked, they carry a current in the same direction, just like this example we were looking at here. We expect them to be attracted together. See that again? But if we swap the direction of one of those wires, so that we do another experiment where the currents are opposed, so maybe we're swapping I2 here, so we expect a negative sign there, and we expect the two wires to move away from each other to be repelled. See that again? We define what an amp is from measuring the force between two wires, and as such we define what a coulomb is too, because that's defined in terms of an ampere. Specifically, we say that we have an amp passing along two long parallel wires 1 meter apart, where they carry the same current, and where we measure force per unit length on each wire to be 2 times 10 to the minus 7 newtons per meter. Using the equation from the last page, we put the numbers in. We say we have an amp only where we measure this force per unit length. And you can see that comes out from that equation. As I say, the coulomb's defined from this too. 1 coulomb has passed at a junction in a conductor per second when we have 1 amp flowing. There are 3 wires carrying currents involved in this problem. 2 are going into the page here as shown, I2. They're infinitely long, distance A apart. A is 1 centimeter. And they're causing this wire above them to be levitated between them. That's because it's carrying a current in the opposite direction. And as we just saw, that means they're going to repel, and they're going to repel. So there's a force of repulsion from the left-hand wire to this wire FB, and a force of repulsion from the right-hand wire to this wire FB. Well, that wire's going to have a weight too, and we're given information about the wire, its mass, for example, and its length. So we've got a force there that we could calculate for its weight too. We should be able to calculate all those forces. And the question is, what current must the infinitely long wires carry so that the 3 wires form an equilateral triangle, as shown, so each side. So yeah, what is I2 then? First, let's find the total magnetic force in the upward direction on the levitated wire. That's the sum of these two here. They're symmetric, so the components horizontally would cancel when adding. We're only going to be left with an upward direction for resultant. Its magnitude is given by component of each one, mu naught I1, I2 over 2 pi a. It's from this equation we were just using, times by the length of that wire, I1. And there's two of those, and they're at cosine theta to the resultant. So we take the components in the vertical direction to get the final value of their sum. Well, the gravitational force here is mg, and the sum of those forces has to equal 0. So we can write that and rearrange for I2. And putting the values in, we get I2 equals 113 amps. The magnetic field far from a current loop is given here. It depends on 1 over z cubed, where z is the distance along the axis of symmetry. If we compare that to the electric field we derived for an electric dipole, that 1 over z cubed too. So there is a certain similarity there in the behavior of the two. Both we're talking about dipoles. Here we have a magnetic dipole measured by mu. Mu is the current in the loop times by the area of the loop. And for a magnetic dipole, P was the value of the charge times the separation of the two equal and opposite charges. So very different phenomena, but both going as 1 over z cubed. At least that's easy to remember. We can note that this magnetic field pattern is analogous to that which you'd find for a permanent magnet. It's the same deal. If you can find the dipole moment for any magnetic dipole, whether it's permanent or whether it's created by a loop here, you can find the magnetic field as a function of distance along this axis of symmetry there by this formula. There are two other ways in which electrons can generate a magnetic field, albeit from the same principle. One is an electron orbiting in an atom, and another is an electron spinning on its own axis. Both really require quantum mechanics to complete a useful description, but let's just look at the magnetic aspects of it. If we consider the Bohr atom, an electron orbiting a positive nucleus from theme 1, it is a simplified description of an atom as we concluded in that theme, but it's useful here. We can talk of an electric current, E over t, the time period. The time period is the circumference divided by the speed. We simplify as EV over 2 pi r. The resulting magnetic dipole moment is I times A from before, so the area of this loop is pi r squared, and the current we've just worked out. We can put that together, we get EVR over 2. We can add an m top and bottom if we choose. We end up with E over 2m, and in brackets here we've made the orbital angular momentum, MRV. So the magnetic dipole moment due to this orbiting electron is minus E over 2m times by the orbital angular momentum. And it's the orbital angular momentum, something that we considered in theme 1 went in steps. You remember that was Bohr's postulate that we'd have to go in steps of h bar. We write a similar formula for the magnetic dipole moment due to an electron spinning on its own axis. Again, we have to turn to quantum mechanics to go deeper. And with quantum mechanics, we find that only quantized values can be found for angular momentum and spin, and so only quantized values can be found for their respective magnetic dipole moments. A solenoid is a loop with a large number of turns that's been pulled apart to form a coil or a helix. Here we have a current coming out then, it's going into the page there, back out here, into the page, the same wire coming back out there, into the page and so on. So this is how it looks. And if we remember our rule for relating the field generated by a current to the current direction, you can see the field lines there going into the page. If a screw was going into the page, we'd have to be turning it clockwise like that. So that's the direction of the field around it. If a screw was coming out of the page, like the current is here, we'd have to be turning the screw anti-clockwise here. So that's the direction of the field there. And you can see that the field contributions are all going to be in the upwards direction from all the wires in the center. So they add constructively in the middle of the solenoid. And that's why we get this pattern like this, which looks like an extended magnet, doesn't it? Extended permanent magnet. Indeed, it is analogous. The magnetic field inside this solenoid is given by mu in the permeability, in vacuum, times by the number of turns per unit length, times by the current in the wire. Let's calculate this magnetic field inside a solenoid now. We're going to use Ampere's law to do it. Integral of B ds equals mu naught I enclosed. We can choose our Amperian loop as we wish. We're going to choose this 1, 2, 3, 4 sides. We can choose this W parameter here to be as large as we like and still enclose the same charge. So we can do that, and if we made it very large, arbitrarily large, then the contribution magnetic field along this length 3 would have to be 0. It will anyway be very small, even immediately outside the solenoid, as we find. But yeah, we can actually say it has to be 0 from that argument. Sides 2 and 4 don't contribute anything to the integral because they're perpendicular to the B field. And so we only get a contribution from side 1. Integral of B ds equals the integral of B, we can take that outside, times the integral of ds. And the integral of ds is just this length L. So we get BL equals mu naught times by the enclosed current. The enclosed current is the number of turns in length L, N, because we're looking at a length L, times by I, the current in the wire. Can we arrange that for B? Get mu naught N over L times I, the number of turns per unit length, which is little n, and that's that equation we had on the last page. If we did choose to take an Amperian loop in this direction here, we could argue that there has to be a current going through that loop, even though that's outside the solenoid. Overall, there's a current that enters one end and exits the other. It's a current not equal to Ni, but just equal to I itself. And so we could find a magnetic field oriented in that direction outside of the solenoid. It would be weak, but it would be present. Here we have a rectangular wire passing through the center of a solenoid. Which of the following statements describes the force, if any, that acts on the rectangular loop when a current is passing through the solenoid and through the wire loop? Now, we're not showing a connection to anything in the wire loop, but we have to take that as read then. A, the magnetic force causes the loop to move upward. The magnetic force causes the loop to move downward. Move to the right, move to the left, or it's not affected by the current passing through the solenoid. Here we have a rectangular wire loop has one side passing through the center of a solenoid. Which of the following statements describes the force of any that acts on the rectangular loop when a current is passing through the solenoid and through the wire loop? So we don't see a connection to the wire loop there, but we have to take that as read. The magnetic force causes the loop to move upward or downward or to the right or to the left, or it doesn't move. Okay, well, we got a current on that wire in the middle. We know there's a magnetic field there. We can calculate that. That's mu naught Ni from the solenoid. The field is aligned along the solenoid. It's in the direction of the wire and the current in it. So L cross B would be 0. Sine theta would be 0 because theta is 0. And so there's no force of the solenoid acting on that wire with the current. Newton's third law tells us equal and opposite. Even though that wire is generating a magnetic field, it couldn't act on the solenoid either. And you can see that also if you think about what that wire is doing in terms of generating a magnetic field. It would be, the magnetic field would be aligned to the wire in the solenoid at every point. And again, the same argument would apply, that it wouldn't exert a force then on the wires of the solenoid because L cross B at every point would be 0. So it's E. Let's now consider the magnetic field in the toroid. It's effectively a solenoid that's been wrapped around on itself. It's a donut, right, with a coil wrapped around it. We've got the current coming out here, going in there, coming out here, going in there, one wire wrapped around. Well, you can see by inspection it's very similar to what you'd expect from a solenoid. You had mu naught Ni for a solenoid, where N was the number of turns per unit length, and if you take the total number of turns, big N, divide by the circumference, then it looks to be coming directly from a solenoid. However, we ought to be a little bit careful here because depending where you take your Amperian loop, either out here or in here, yes, it really is going to give you a different value of B, It depends on where you are inside the toroid. And that really isn't predicted directly from the consideration of a solenoid, is it? So we ought to just be a bit careful and actually do the Amperian loop and apply Ampere's law. So the integral of B ds then for this case is B times by the integral of ds around the Amperian loop there. We can take B outside because why would it be different here, from here, from here, from here, by symmetry? And that's going to be this 2 pi rb then, where r is the distance from the center to the Amperian loop, and that can be anywhere inside the toroid. Well, the enclosed current by that loop is everything inside here, right? So it is the total number of turns in the toroid times by the current in the wire. We can put that in for Ampere's law. There we have it. We arrange for B, and we get this equation. And yes, it is true that as you change the radius, the magnetic field is going to get weaker as you increase it, and it's stronger on the inside of a toroid. That concludes this theme 3.1, the first part of magnetism. We introduced the idea of magnetic fields, a force and a moving charge, which led us to the motion of charges in a magnetic field, and a mass spectrometer. Consider the force on a wire with a current, the torque then on a wire loop, and a DC motor. Came to the idea of magnetic dipole moment, and then we turned to think about magnetic fields generated by currents and Ampere's law. The forces between wires came from that, and the field due to a loop, a solenoid, and a toroid. Well, I hope you found that useful. Now, the problems associated with this theme 3.1 are available, so it's a good time to be getting onto those.